Okay, so we are the autonomous self-driving wheelchair team, and here's our video demo. So this quarter, we were exploring how we can design a wheelchair that gives freedom of mobility back to the user of the wheelchair. So our solution was to develop a task manager system to switch effectively between the Skyline system and switch the direction of the Skyline system when detecting April tags. And we also improved the Skyline algorithm efficiency and robustness to ensure the switching of the direction of the Skyline efficient what system was accurate. And we also compared the most efficient LiDAR odometry packages to ensure accuracy for future teams when using those packages. So one of the main components of the Skyline system is the Arduino. So Arduino is further down the system at closer to the hardware level. So the Arduino receives signals from the main PC in the form of the PID controller and the task manager. And it uses raw serial connection to subscribe to these tasks from the PC. And it maps these signals into accurate PWM signals for then conversion into DC voltage by the external circuit board connected to the Arduino. And then the left arm of the wheelchair receives these signals from the circuit board and then will drive the wheelchair. It receives these signals at the direction and velocity pins.
Representative line from detected segments to serve as a reliable reference for detecting the drift of the wheelchair. The first is the line segment detection. So to detect the line segments above the wheelchair, we deploy the pre-trained line segments detection deep learning model. Instead of simple edge detection, this model is designed to detect line segments that correspond to some geometric structures such as parallel lines, vertical structures, and intersections which can be commonly found in the interior of the buildings. Furthermore, this model is lightweight enough to be suitable for resource-constrained environments. So as you can see in the video, this model could allow us to successfully detect line segments under edge device in real time. The second is best line selection. To select the most reliable line segments among all, we design a weighted scoring system to assign a credit score to each candidate line. First, we prioritize lines that are close to 90 degrees, because 90 degrees corresponds to the forward direction of the wheelchair's motion. And then we prioritize line segments located in the center part of the image, as these are more likely to correspond to the sitting area directly above the wheelchair's path. And then we also take into account the length of the line, because longer lines tend to be more structurally reliable for autonomous navigation. Finally, we select the best line by evaluating each candidate's vectors, where a weighted linear combination is used to assign scores and rank the candidates accordingly. The last is IOU-based previous baseline tracking. If we only perform baseline detection independently for each frame, the selected line segments may vary significantly across time. This can cause abrupt changes, which may disrupt the PID controller and break the path planning process. So here we use IOU-based previous baseline tracking to maintain the temporal consistency of the baseline across frames. In each new frame, we compare the previously selected baseline with all current candidates by computing their intersection over union after extending both lines to the full image height. If a sufficiently similar line is found, we reuse it as the baseline for the current frame. Otherwise, we select the new one using the same weighted criteria. As you can see in the video, deviations in the selected line segments can occur between consecutive frames when no previous line tracking is applied. The IOU-based tracking significantly mitigates this issue by ensuring smoother and more consistent line selection across the frames.
Okay, so for the PID controller, you can see we use two PID controllers to control the wheelchair. One is the angular PID and the other one is the lateral PID. And we subscribe to these rules topic. One is the slope of the current baseline. The other is the center coordinates of the current baselines. These are two key values we are going to pass to the PID controller to correct the wheelchair. So in the normal control loop, we would use this angular PID. And the way we pass arrow is, as you can see in the drift callback method, we would get the current angle of the slope, and we would subtract this value by 90 degrees, which is the desired best align angle appeared in the camera. And once we get this arrow, we pass this arrow to the angular PID controller. And in a normal control loop, this PID controller would generate an output and publish this the rows topic, so the wheelchair can make adjustments accordingly. And another PID controller is called the lateral PID. what it does is it eliminates the lateral drift, and as you can see, it will be activated through this callback method, which would keep track of the center coordinates of the baseline and calculates its lateral arrow in the meantime. So if the lateral model is not activated and the absolute value of the lateral arrow is larger than the threshold we set, which now is 300 pixels, it's a very big value. Of course, you can tune this value, set it to smaller, so the lateral PID will be activated more frequently. And if this is true, we would activate this lateral PID. So the lateral PID would begin to work. So in the meantime, the normal angular PID will be shut down. As you can see, this line will not be executed. So in the control loop, it would execute this if statement. So once the center of the baseline re-enters the threshold, this lateral PID will be shut down and return to the normal angular PID. And here's another method I should also talk about. It's the April tag callback method, which would receive topics from the rows core. So if the message is to deactivate this PID controller, then the entire PID controller will be shut down, and the Arduino mounted on the wheelchair would start to send command to the wheelchair directly, make it turn 90 degrees or 180 degrees, depends on the type of the April tag detected. Once the turn is complete, it will send another message data called activate. In this case, this PID controller would reactivate. And in the meantime, we set the lateral door PID to remain dormant for another extra 8 seconds to avoid overcorrection.
This is the Skylane Task Manager and April Tag system. The Task Manager is a functional state machine design with 4 distinct states that progress in the following order: line following, tag detected, turning, and returning to line. The wheelchair mainly exists in the line following and turning state, as the line following state is when it is following the lines along the ceiling and using a PID controller to minimize drift, and the turning state is when an April tag has been detected and the wheelchair is rotating. The tag detected and returning to line states are purely transitionary and used to signal the Arduino and PID controller that either an April tag has been detected and it is time to turn, or that the April tag turn has been completed and it is time to resume line following. April tag detection takes precedence over the PID controller. When a tag is detected, it interrupts the PID controller immediately to begin the turn as specified by the April tag's ID. While the chair is turning, the PID is shut off to prevent any drift correction from being done and to make sure that it does not become confused due to the new pose of the wheelchair. We also added suitable buffer time after a tag is detected to prevent it from being double detected. The April tags are 2D barcodes similar to QR codes with distinct IDs that correlate to a tag description. We use 3 different April tags from the 36H11 tag family that represent 90-degree right, 90-degree left, and 180-degree turns for IDs 0, 1, and 2 respectively. We detect the tags that are placed on the ceiling using a ceiling-facing camera connected locally to the host PC to minimize latency.
Hi, I'm Jerry Khan from the LiDAR odometry team, and our task was to evaluate the LiDAR odometry methods, especially the RF2O and RedMap, against the vision-based odometry using a single camera RTMap setup. We performed thorough tests by driving our wheelchair along predefined paths ranging from 20 to 50 to 500 meters within an indoor hallway environment. And using the EVO trajectory tool, we compared the trajectories in both short-range and mid-range scenarios. Our results indicated that the RF2O delivers strong performance in the shorter loops, but it shows increased drift over long paths. It is defined as the most reliable odometry solution for indoor navigation.
So for our wheelchair integration, at the top, we mounted a 2-meter high LiDAR pole to assist with obstacle detection and odometry. We also placed 2 ceiling-facing cameras. One is used to reduce the odometry drift by tracking ceiling features, and the other feeds information to our task manager to detect April tags. On the side of the wheelchair, you'll see 4 fourth-angle cameras. These aren't currently active, but are set up for future perception tasks like object recognition or SLAM. To organize and simulate everything virtually, we created a detailed URDF model that defines the wheelchair structure and the exact sensor placements. You can see a visual of this model on the far right. Lastly, to protect our onboard electronics, we used lightweighted foam board to enclose the back of the wheelchair, making it both modular and accessible.
Hi, I'm Mo from the LiDAR odometry team and wheelchair integration team. Besides testing odometry with the RF2O package and R-type map, we are also working on the connected ICP package. This package aims to enhance odometry by combining non-wheel odometry with LiDAR inputs. As you can see, the original wheel odometry produced unreliable results. But after applying connected ICP with LiDAR inputs, the system generates a smooth, coherent trajectory as expected. But we don't have real issue is that we don't have wheel encoders in our system. So we are using data provided by Cyberworks company to test our results. As you can see, the left-hand side is the connected ICP and the right-hand side is RF2O. And RF2O maintains acceptable deviations levels, but on contrary, connected ICP shows significant deviation from the expected path. So based on this result, we believe that connected ICP package requires additional parameters tuning to achieve better performance.